Welcome everyone to Wits Tutoring Group. Today I want to talk a little bit about Gibbs free energy. We call this the change of Gibbs free energy or just free energy. Now, everything in the universe, every substance and every reaction has a positive, negative, or sometimes zero change in free energy. The important part is that when something or through a process we lose Gibbs free energy, aka a negative change, we call that a spontaneous process. You can think of that as if I let go of a bowling ball 10 feet above the ground, it's going to spontaneously fall. Therefore, it was a negative change of Gibbs free energy. The other option would be positive. That would be a non-spontaneous process. One of the most important formulas when describing Gibbs free energy is Gibbs free energy is equal to the change of enthalpy minus temperature times the change of entropy. And let me zoom in a little bit and write those out. This is enthalpy. This is temperature. I want to mark that that's in Kelvin, by the way. And this is entropy. Now, first of all, I want to say something, because when we're talking about this math or kind of understanding it, it's less important about the actual numbers that may come into play eventually, but we're caring more about whether or not things are positive or negative. I want to point out that temperature is always positive if we're in Kelvin or an absolute temperature scale. But enthalpy can be positive or negative. Entropy can be positive or negative. With those two switches, there are 4 options that can happen. Now, I want to borrow something from biology. I call this the Punnett square, Gibbs free energy. So delta H, or enthalpy, change of enthalpy can be positive or negative, and change of entropy can be positive or negative. I'm going to write some dividers in here. Let's start with this top right square. In this square, we have delta G is equal to delta H minus T times delta S. So we have, in this top right square, we have a negative value minus temperature, which is always a positive value, times a positive value of delta S, because it's up here. Let me get everything in frame. So let's talk about this equation for a second. We have a negative value minus what's a positive times a positive? Well, that's still a positive value. All right, so I'm just kind of simplifying it. And then we have a negative value minus a positive value. It's the same thing as adding a negative value. I think this makes it really clear. If we have something in this top right quadrant, no matter what, delta G will equal a negative number plus a negative number, aka it is always negative. So I'm going to put in this top right quadrant that delta G is negative, or that if delta S is positive and delta H is negative, we will always be spontaneous. Perfect. Let's do the opposite. Let's do this bottom left quadrant. Let's go through the math again. In this bottom right quadrant, we have a positive value for delta H minus a positive times a negative. Well, that's the same thing as, let's deal with the multiplication first, minus a negative value, which, when we simplify again, is a positive number plus a positive number. In other words, if we're in this bottom right quadrant or situation, delta G will be positive no matter what, which means it will always be non-spontaneous. Another way of saying that is it will never be spontaneous, but we usually like to, I don't know why, we keep it as that always phrase. Now this top left and bottom right quadrant are a little bit more interesting. let's walk through the top right quadrant. In this top left quadrant, in here we have a positive number minus a positive times a positive. If we do the same simplification we've been doing, that turns to this. Now, is a positive number plus a negative number always going to be positive or always going to be negative? No, it depends. What does it depend on? Finally, we're going to talk about temperature. You see, temperature is this value right here that we've kind of been waving our hands away from. But if we increase temperature, it's like we're making this value on the right side more important. So the bigger temperature gets, the more, we call this the entropy term. Why? Because that's entropy. That gets bigger in magnitude. And eventually it tips the scales and it becomes delta G becomes negative. So we say at high temperatures, delta G is negative, or we have something that's spontaneous. Now, if we decrease the temperature, eventually this positive side is going to win out. We have something positive. Excuse me. So we say at low temperatures, delta G is positive, and we have a non-spontaneous process. Now, when I say high and low temperatures, that depends on the situation always. So, for example, let's talk about water boiling. Does water boil spontaneously at room temperature? No, that would be a non-spontaneous process. But at 500 degrees Celsius, does water boil? Yes, that would be a spontaneous process. Therefore, we know that this process is temperature dependent, and it makes sense because, in fact, when we boil water, enthalpy change is positive and entropy change is positive. So that's an example of a situation in which spontaneity depends on temperature. Now, you can probably guess in this bottom right quadrant is the exact opposite of the top left. At high temperatures, delta G will be positive, or we have a non-spontaneous process. And at low temperatures, low temp, delta G will be negative, and we have a spontaneous process. Think of water freezing. Will water spontaneously freeze at room temperature at a high temperature? No, but it will spontaneously freeze at like negative 200 degrees Celsius. So that is another situation. It's kind of the opposite of that top left quadrant. Perfect. So I want to talk about how to use the signs of delta H and delta S to determine delta G and the spontaneity of a process.